Alright, let's go. In 2006, we took Pluto's name away. We called it a dwarf planet, moved on, and left it at the edge of the solar system like a world that no longer mattered. But Pluto never stopped changing. Beneath that frozen surface, nitrogen ice moves. Above it, a thin atmosphere rises into space. And surrounding the entire world is a haze created by complex chemistry, driven by sunlight and radiation. Then humanity looked at Pluto in a completely different kind of light. And suddenly, the little world we thought we understood became much stranger. Because Pluto is not simply frozen, it is chemically active. Its atmosphere changes with the seasons. Its surface exchanges material with the sky above it. And its hazy atmosphere can actually influence how Pluto loses heat to space. The world we demoted in 2006 was a world we had barely seen. And the more closely we look at Pluto, the more obvious one thing becomes. We may have been asking the wrong question all along. To understand why, we have to go back to the moment Pluto lost its title. For generations, Pluto was the 9th planet. It was the strange little world at the edge of the solar system, so distant that even powerful telescopes could reveal very little about it. Children learned its name. Textbooks placed it beside the other planets. And then astronomy changed. Scientists began discovering more objects beyond Neptune. The region wasn't empty. It was filled with icy bodies, leftovers from the formation of the solar system, moving through a vast region called the Kuiper Belt. And suddenly Pluto wasn't alone. It was part of something much bigger. That created a problem. If Pluto was a planet, what about the other large objects in the same region? Where exactly should the definition end? In 2006, the International Astronomical Union established a formal definition of a planet. Pluto met some of the requirements. It orbits the Sun. Its gravity is strong enough to make it nearly round, but it had not cleared most of the other objects from its orbital neighborhood. So Pluto was reclassified, a dwarf planet. To millions of people, it felt like a demotion. But there was something almost ironic about the timing. We were arguing about what Pluto should be called at almost exactly the moment when technology was finally becoming powerful enough to show us what Pluto actually was. We had never seen its surface up close. We had never examined its atmosphere in detail. We had never watched its strange frozen landscape from nearby. We had never understood the chemistry happening above its surface. We had judged a world we had barely visited. And then New Horizons arrived. After traveling for almost a decade through the darkness of the solar system, the spacecraft finally reached Pluto in 2015. What it saw changed the story. Pluto was not a dead ball of ice. There were mountains, there were valleys, there were enormous frozen plains, there was nitrogen ice, there was methane, there was carbon monoxide, and there was something nobody expected to see on such a distant, tiny world. A giant heart, Sputnik Planitia. A vast bright region covering part of Pluto's surface, surrounded by terrain that looked anything but simple. Some of Pluto's landscapes appeared remarkably young. Ice was moving. Materials were being exchanged between the surface and atmosphere. And above it all was a thin blue atmospheric haze. Pluto had weather, not weather like Earth. There are no ordinary rainstorms sweeping across its surface. Instead, Pluto's climate is controlled by gases and ices that can move between the atmosphere and the ground. And because Pluto takes about 248 Earth years to complete one orbit around the Sun, its seasons unfold on a timescale almost impossible for humans to experience. A season can last for decades. The atmosphere can change as Pluto moves farther from or closer to the Sun. Surface ice can sublimate into gas, and later, that material can freeze again. The world that looked like a frozen rock from Earth was actually running a slow planetary cycle. But this was still only what New Horizons could see. There was another layer of Pluto's story hiding in invisible light. And that is where the James Webb Space Telescope enters the picture. James Webb does not see the universe the way human eyes do. It sees infrared light, and that matters because infrared can reveal information about temperature, chemistry, and molecules that ordinary visible light images cannot show. For Pluto, this was especially important. This is a world where temperatures are incredibly low, where nitrogen can exist as surface ice, and where the atmosphere is so thin that its behavior is difficult to understand from ordinary observations alone. Webb could examine Pluto's thermal emission. It could look at wavelengths carrying information about the energy coming from this distant world, and the result revealed something remarkable about Pluto's haze. The haze was not simply sitting there as a beautiful layer around the planet. It was participating in Pluto's energy balance. And this is where the story gets strange. Pluto's atmosphere contains nitrogen and methane. When sunlight and energetic radiation interact with those molecules, they can break apart and trigger chemical reactions. Those reactions create increasingly complex carbon-rich compounds. Eventually, particles form. Those particles contribute to Pluto's famous reddish brown haze. These substances are often described as tholin-like materials. The word sounds like something from science fiction, but the chemistry is real, and the important part is not simply that Pluto has this haze, it is what the haze does. The particles can absorb radiation and emit energy at infrared wavelengths. That allows energy to escape from Pluto into space. In other words, the haze acts as part of Pluto's natural cooling system. Think about what that means. The sun is incredibly distant. The sunlight reaching Pluto is already enormously weaker than the sunlight reaching Earth. The surface is frozen. The atmosphere is extremely thin. And yet a layer of microscopic particles created through atmospheric chemistry can influence how efficiently the atmosphere loses heat. Pluto does not have to be alive to do something that sounds almost alive. It simply needs physics. Sunlight drives chemistry. Chemistry creates haze. The haze interacts with radiation, and infrared energy escapes into space. The result is atmospheric cooling. Research has suggested that Pluto's haze may be a major factor controlling the temperature structure of its atmosphere. Without that haze, models indicate that the atmosphere could behave very differently. With the haze present, Pluto has an efficient way of radiating energy away. So when we say Pluto is cooling its own atmosphere, we are not talking about a mysterious force. We are talking about a natural planetary system. But the strange part is how complicated that system becomes when you follow the molecules. The chemistry begins high above the surface. Methane and nitrogen interact with sunlight and energetic particles. New compounds form. Some of those compounds eventually become part of the haze. The haze absorbs and emits energy. Some particles can move downward. And material from Pluto's atmosphere can interact with the surface. The atmosphere and surface are connected. The sky is not separate from the ground. They are part of the same cycle, and that cycle is controlled by Pluto's enormous distance from the Sun and its extraordinarily long seasons. When Pluto moves through its orbit, the amount of solar energy it receives changes. That can affect surface temperatures. Surface ices can change state, atmospheric pressure can change, and gases can move between the surface and atmosphere. It is a climate system unlike anything on Earth, but it is still a climate system. And there is another consequence of Pluto's extreme environment. Its atmosphere does not remain perfectly trapped around the world forever. Some material can escape, slowly, molecule by molecule, and once that material leaves Pluto, it enters the darkness surrounding the planet. This is where the story takes another turn, because Pluto is not completely isolated from the other world that shares its strange corner of space. Its largest moon is Charon, and Pluto and Charon are not an ordinary planet and moon pair. They are much closer to a binary system. Their relationship is so unusual that the center around which they orbit lies outside Pluto itself, two frozen worlds locked together by gravity. And material from Pluto can become part of the story of Charon. Pluto's atmosphere is incredibly thin, and because Pluto has much weaker gravity than Earth, particles high in its atmosphere can eventually escape into space. This is called atmospheric escape. It does not mean Pluto is suddenly disappearing. It is not losing its atmosphere in some catastrophic event. The process is slow, extremely slow. But over enormous periods of time, even a slow process matters. Gas can leave Pluto. Some of that material can travel through the environment surrounding the Pluto-Charon system. And this makes the relationship between the two worlds even more interesting. Charon is about half the diameter of Pluto, making it enormous compared with most moons relative to their parent body. The two worlds orbit a common center of mass. They are gravitationally connected in a way that makes the system look almost like two frozen worlds dancing around one another. And Charon has its own strange surface. Its landscape contains water ice and other materials, while its northern polar region has a distinctive reddish appearance. Researchers have investigated whether material originating from Pluto can contribute to this coloration. One proposed mechanism involves methane escaping from Pluto and reaching Charon, where intense radiation can transform the material into more complex organic residues. So something that begins in Pluto's atmosphere may eventually influence the surface of Charon. A molecule leaves one world. It crosses the space between them, and under different conditions, chemistry changes what happens next. There is something almost poetic about that. Pluto is not simply orbiting alone at the edge of the solar system. It is part of a connected environment. Its atmosphere interacts with space, its surface interacts with its atmosphere, and its largest moon may interact with material originating from Pluto. Nothing happens quickly, nothing happens dramatically, but the solar system does not need to move quickly. It has billions of years. That is enough time for tiny processes to transform worlds, and Pluto is full of those processes. Its atmosphere contains nitrogen, it contains methane, it contains carbon monoxide, And observations have revealed more complex hydrocarbons as well. These molecules are important because they show that Pluto's atmosphere is chemically active. Radiation is constantly interacting with the gases. Molecules are being broken apart. New molecules form. Particles grow. Haze develops. And some of those materials eventually settle toward the surface. Pluto is essentially running a natural chemistry experiment in an environment colder and darker than almost anything we experience on Earth. The ingredients are simple: gas, ice, radiation, sunlight, and time. But the results are surprisingly complicated, and this is where we need to separate what we know from what we still don't know. Because the original story about Pluto has often been exaggerated. There is no confirmed evidence that James Webb discovered an alien molecule hiding in Pluto's atmosphere. There is no confirmed mysterious chemical fingerprint proving that Pluto and Titan contain the same unknown substance. And Pluto's atmosphere is not literally a poisonous sky raining deadly chemicals onto the surface. Those descriptions make the story sound terrifying, but the real science is already strange enough. The actual mystery is more subtle. We still do not understand every detail of how Pluto's haze forms, grows, moves, and interacts with the atmosphere. We are still learning how its complex organic chemistry affects the climate. We are still trying to understand how energy moves through such a thin atmosphere. And we are still learning how Pluto's atmosphere changes as the dwarf planet travels through its enormous seasonal cycle. The deeper problem is that Pluto gives us very little time to observe change. A human lifetime is almost nothing compared with Pluto's 248-year orbit. We cannot simply watch an entire Pluto year and see what happens. We have to reconstruct its climate from observations taken at different times. New Horizons gave us a close look at the surface. Earth-based telescopes gave us years of monitoring. And now infrared observations are giving us another layer of information. Different instruments, different wavelengths, different pieces of the same puzzle. And the puzzle is still incomplete. But there is one thing that has already become clear. Pluto is not a static world. It is changing. Its atmosphere changes. Its surface changes. Its chemistry changes. And its relationship with space changes. The strange thing is that we almost missed all of it. Because while we were arguing about whether Pluto deserved to be called a planet, the world itself was quietly doing what worlds do: changing, cycling, reacting, and losing material to space. That is the part of Pluto's story that should change the way we think about the solar system. For a long time, we imagined planets as the important worlds and everything else as leftovers, but Pluto destroys that simple picture. Because if a world this small can have an atmosphere, weather, complex organic chemistry, moving ice, seasonal cycles, atmospheric escape, and a thermal system controlled partly by haze, then size does not tell us how interesting a world can be. Pluto is small, but small does not mean simple, and cold does not mean dead. That distinction matters far beyond Pluto. Because Pluto belongs to the Kuiper Belt, and there are many other icy bodies out there. Most of them are much harder to study. They are smaller. They are farther away. Their atmospheres, if they have them, are extremely difficult to detect. Their surfaces are barely visible from Earth. And yet Pluto has shown us that distant icy worlds can contain surprisingly complicated chemistry and climate processes. So how many other worlds are doing something similar? How many have atmospheres too thin for our older instruments to detect? How many have surface ices that move with the seasons? How many contain organic chemistry created by radiation? And how many are changing right now while we simply cannot see it? This is why James Webb matters. Not because it turned Pluto into a planet again. It didn't. And not because it discovered some supernatural mystery. It didn't. It matters because it gives us another way to investigate a world that was once almost impossible to study. Visible light tells us one story. Infrared tells us another. Spectroscopy tells us another. And when all those pieces are combined, Pluto becomes much more than the tiny point of light we used to know. It becomes a physical system, a world where sunlight can create chemistry, where chemistry can create haze, where haze can affect heat, where heat can escape into space, where atmospheric molecules can leave the planet, and where some material may eventually influence its largest moon. Every step connects to the next, and that is what makes the story so strange. There is no single monster hiding on Pluto. The monster is the complexity itself. A tiny world at the edge of the solar system is running processes that require us to think about atmospheric physics, radiation chemistry, thermal emission, surface geology, orbital cycles, and planetary evolution all at once. And we are trying to understand all of that from billions of kilometers away. Then there is Pluto's famous heart, Sputnik Planitia. It looks like a symbol, almost as if Pluto is staring back at us. But beneath that beautiful appearance is an enormous geological system. The basin contains volatile ices. Those ices can participate in atmospheric cycles. Heat from within Pluto may also play a role in maintaining some of the geological activity we observe. And that creates another uncomfortable thought. We often imagine the outer solar system as a place where everything froze billions of years ago and simply stayed that way. But Pluto tells us that the outer solar system may be much more dynamic. Ice can move, atmospheres can change, chemistry can continue, radiation can reshape molecules, and worlds can evolve even when they receive very little sunlight. The sun does not have to provide all the energy. Internal heat matters, radiation matters, gravity matters, chemistry matters, and time matters more than almost anything else. Give a world billions of years, and tiny processes can create enormous consequences. That is what makes Pluto such an important scientific target. Not because it is secretly a planet, not because scientists regret the 2006 decision, but because it is a natural laboratory. A laboratory where the conditions are completely different from Earth. A place where nitrogen becomes ice, where methane becomes part of atmospheric chemistry, where radiation builds complex carbon-rich material, where haze can affect the temperature of the atmosphere, and where an atmosphere can slowly leak into space. The more we learn, the harder it becomes to call Pluto a frozen rock. It is a world. A small one, a distant one, a strange one, but a world nonetheless. And the most interesting part may be what comes next, because Pluto is not the end of the story. It may be the beginning of a much bigger one. For decades, Pluto represented the edge of what we knew. It was a distant dot, a mysterious ninth planet. Then it became a dwarf planet, and many people assumed that was the end of the story. But the opposite happened. The closer we looked, the more complicated Pluto became. New Horizons showed us mountains where we expected emptiness. It showed us moving ice where we expected frozen stillness. It revealed an atmosphere where we expected almost nothing, and now infrared observations are helping us understand how that atmosphere interacts with radiation and loses heat. The world we once reduced to a single word turned out to contain an entire system. And maybe that is the real lesson of Pluto. We often confuse classification with understanding. We give something a name and feel like we have explained it. Planet, dwarf planet, moon, asteroid, comet. But a label tells us what category something belongs to. It does not tell us what that world is doing. Pluto is proof. We knew its name long before we understood its nature. We knew where it was before we knew how its atmosphere worked. We knew it was small before we knew how active its surface could be. And we called it a planet before we had ever seen it properly. Then, after we changed the label, we finally sent a spacecraft there. And Pluto answered with a landscape that looked almost impossible. Now we are studying its atmosphere in infrared. We are learning about its haze. We are studying the chemistry of its gases. We are investigating how energy moves through its atmosphere. We are watching how material can escape. And we are discovering that even at the edge of the solar system, worlds are not simply frozen in time. They evolve, they interact, they change, slowly, silently, over periods so long that an entire human civilization can appear like a moment. And that makes Pluto's story strangely personal. Because in 2006, we thought we had finished the conversation. We thought Pluto had been understood well enough to be placed into a smaller category. But the universe did not care about our argument. Pluto kept moving. Its atmosphere kept changing. Its haze kept forming. Its ice kept shifting. Its molecules kept reacting. And its energy kept escaping into space. We changed the label. Pluto changed nothing. And now, almost 2 decades later, we are still discovering things about the world we thought we had already figured out. That should make us wonder about everything else. If Pluto is this complicated from the beginning, what about the countless worlds we have never visited? What about the icy bodies beyond Neptune? What about the objects so distant that even our most powerful telescopes see them as tiny points of light? What is happening on their surfaces? What chemistry is taking place in their atmospheres? What worlds are changing while we are looking somewhere else? The solar system may be far more active than it appears, and Pluto is one of the clearest reminders. It sits billions of kilometers from the sun. It receives only a tiny fraction of the sunlight that reaches Earth. Its atmosphere is incredibly thin, its temperatures are brutally cold, and yet it has weather, it has chemistry, it has geology, it has seasons, it has atmospheric escape, it has a haze that can influence its thermal environment, and it has a giant moon with which it shares an extraordinary gravitational relationship. That is not a dead rock. That is a world, a strange one, a distant one, a world we almost stopped paying attention to, and perhaps that is why Pluto is so fascinating. Not because it was once the 9th planet, not because it deserves a sentimental apology, but because it taught us something much more important. The universe does not become less interesting just because something becomes smaller, and a world does not stop being a world because we change the name written beside it. In 2006, we looked at Pluto and decided it no longer counted as a planet. Years later, we looked again, and we discovered that we had barely been looking at Pluto at all. The frozen world at the edge of the solar system was never silent. We were. And now that we are finally listening, Pluto has a lot more to tell us. If this video changed the way you see Pluto, then stay with us. Because at the edge of the solar system, there are other worlds waiting in the darkness. And if Pluto could hide this much from us, the next one might be even stranger. Alright, see you in the next one.